General Physics 1, Quarter 2, Module 2, Rotational Equilibrium and Rotational Dynamics. Lesson 1, Newton's Law of Gravitational. What is Newton's Law of Gravitational? Newton knew that the force that caused the apple's acceleration must be dependent upon the mass of the apple, and since the force acting to cause the apple's downward acceleration also causes the Earth's upward acceleration, that force must also depend upon the mass of the Earth. So for Newton, the force of gravity acting between the Earth and any other object is directly proportional to the mass of the Earth, directly proportional to the mass of the object, and inversely proportional to the square of the distance that separates the centers of the Earth and the object. Equation of law of gravitation. Here, F is the magnitude of the gravitational force on either particle. M of 1 and M of 2 are their masses. R is the distance between them, and G is a fundamental physical constant called the gravitational constant. The numerical value of G depends on the system of units used. This equation tells us that the gravitational force between two particles decreases with increasing distance r. If the distance is doubled, the force is only fourth as great, and so on. Although many of the stars in the night sky are far more massive than the sun, they are so far away that their gravitational force on the Earth is negligibly small. What is the importance of Newton's law of universal gravitational? We can calculate the force or pull of gravity of the planets and universe. We can also determine the trajectory of astronomical bodies and to predict their motion. It pulls all the objects towards the Earth, the motion of planets around the Sun. Determining the value of G. To determine the value of the gravitational constant G, we have to measure the gravitational force between two bodies of known masses, M of 1 and M of 2, at a known distance r. The force is extremely small for bodies that are small enough to be brought into the laboratory, but it can be measured with an instrument called a torsion balance, which Sir Henry Cavendish used in 1798 to determine G. The figure below shows a modern version of the Cavendish torsion balance. A light rigid rod shaped like an inverted T is supported by a very thin, very quartz fiber. Two small spheres, each of mass m of 1, are mounted at the ends of the horizontal arms of the T. When we bring two large spheres, each of mass m of 2, to the position shown, the attractive gravitational forces twist the T through a small angle. To measure this angle, we shine a beam of light on a mirror fastened to the T. The reflected beam strikes a scale, and as the T twists, the reflective beam moves along the scale. After calibrating the Cavendish balance, we can measure gravitational forces and thus determine G. The presently accepted value is shown below. Gravitational force. The gravitational force is a force that attracts any two objects with mass. In fact, every object, including you, is pulling on every other object in the entire universe. This is called Newton's universal law of gravitation. Example of gravitational force is a ball thrown in the air, comes back to the surface due to Earth's gravity. Calculating gravitational force. Example, the mass m of 1 of the small spheres of a Cavendish balance is 0.100 kg. The mass m of 2 of the nearest largest sphere is 0.500 kg, and the center-to-center distance between them is 0.0500 meter. Find the gravitational force F of g on each sphere due to the other. Solution. Because the spheres are symmetric, we can calculate F of g by treating them as particles separated by 0.500 meter. Each sphere experiences the same magnitude of force from the other sphere. We use Newton's law of gravitation to determine F of g. Gravitational attraction. The force of attraction between all masses in the universe, especially the attraction of Earth's mass for bodies near its surface. Acceleration due to gravitational attraction. Example. Suppose the two spheres in the previous example are placed with their center 0.500 meter apart at a point in space far removed from all other bodies. What is the magnitude of the acceleration of each relative to an inertial system? Solution. Each sphere exerts on the other gravitational force of the same magnitude F of g, which we found in the previous example. We can neglect any other forces. The acceleration magnitudes A1 and A2 are different because the masses are different. To determine this, we'll use Newton's second law. Lesson 2. Gravitational field. What is gravitational field? The gravitational field is the gravitational force per unit mass that would be exerted on a small mass at that point. It is a vector field and points in the direction of the force that the mass would feel. Example of gravitational fields. Gravitational field lines show which ways an object within the field will move. Gravitational field lines on the surface of Earth pull masses straight down, and gravitational field lines in space pull masses towards the Earth. What is the importance of gravitational field? In physics, a gravitational field is a model used to explain the influences that a massive body extends into the space around itself, producing a force on another massive body. Thus, a gravitational field is used to explain gravitational phenomena and is measured in newtons per kilogram. Lesson 3. Gravitational potential energy. What is gravitational potential energy? Gravitational potential energy is energy an object possesses because of its position in a gravitational field. The most common use of gravitational potential energy is for an object near the surface of the Earth, where the gravitational acceleration can be assumed to be constant, about 9.8 meter per second squared. Since the zero of gravitational potential energy can be chosen at any point, the potential energy at a high above that point is equal to the work which would be required to lift the object to that height with no net change in kinetic energy. Since the force required to lift it is equal to its weight, it follows that the gravitational potential energy is equal to its weight times the height to which it is lifted. Lesson 4. Orbits. What is orbits? An orbit is a regular, repeating path that one object in space takes around another one. An object in an orbit is called a satellite. A satellite can be natural, like Earth or the Moon. Most of the objects orbiting the Sun move along or close to an imaginary flat surface. What is the importance of orbits? Recall that the path of an object under the influence of gravity through space is called its orbit. Whether that object is a spacecraft, planet, star, or galaxy. An orbit, once determined, allows the future positions of the object to be calculated. Lesson 5. Kepler's Law of Planetary Motion. What is Kepler's Law of Planetary Motion? They describe how planets move in elliptical orbits, with the Sun as a focus. A planet covers the same area of space in the same amount of time, no matter where it is in its orbit, and a planet's orbital period is proportional to the size of its orbit. What is the importance of Kepler's law of planetary motion? Kepler's law of planetary motion marked an important turning point in the transition from geocentrism to heliocentrism. They provide the first quantitative connection between the planets, including Earth, but even more they mark a time when the important questions of the times were changing. Law of orbits. The law of orbits. All planets move in elliptical orbits, with the Sun at one focus. Law of areas. The law of areas. A line that connects a planet to the Sun sweeps out equal areas in equal times. Law of periods. The law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit.